Ladies and gentlemen, welcome to the lecture series on EC 393, that is Digital Signal Processing. In today's lecture, we shall be concentrating upon the digital filter designs. Okay. Now, before going into the filter designing part, let us first acquaint ourselves with the characteristics, or should I say the responses, or the various aspects of signals and system. Now, the first term that comes to mind is filtering characteristics, which essentially describes how a system changes the amplitude and the phase. So it describes how the amplitude and phase of each input frequency component. So essentially, filtering characteristics describes how a system changes the amplitude and phase response of each of the input frequency components when given to that system. Now, the quantification of these filtering characteristics, is given by the term filter responses. So, in the previous part of this lecture series, I have shown in various mathematical problems how to determine the amplitude and the phase response, or the amplitude, magnitude, and the phase plots of various signal for various types of transform. This will be essential in the designing of our digital filters. So now let us observe how the amplitude and the phase of the system changes due to the relationship between the input and the discrete LTI system. So suppose x of z is a signal in the z domain, b equal to z to the n is given as input to the system, where the system has a transfer function h of z. So evidently the output y of z will be equal to h of z times z to the n. This is in the frequency or the z domain. So if it was in the time domain, say x of n is given as input, then the output y of n will be equal to h of n convoluted to x of n, where we use the property of convolutions for various types of transforms, where it is clearly mentioned that a signal, when convoluted in the frequency domain, will be multiplied in the time domain, and the converse is also true. Now then, let us consider a system having an input x of z in the z domain as mentioned over here, and the system transfer function h of z, so and so. The output will be y of z. So now what we can show is that if the input x of n is equal to cos of omega n plus theta, where omega is the frequency, rather the angular frequency, and theta is just a phase shift. Then y of n can be written as the amplitude of h of e to the j omega cosine of omega n plus theta plus angle of h of e to the j omega. So we will try and prove that y of n will be equal to this expression, which is dependent on the frequency response of the transfer function, both in the magnitude and the phase aspect, where evidently it is already known to us the amplitude will be changed by h of e to the j omega, which is nothing but the magnitude response of the DTFT of h of n. Earlier, in case of DTFT, ft of say x of n, we have written it as x of e to the power j capital omega. But for this filter response or filter design section, I shall be using the notation of small omega. You can use any one, that is not concerned at the moment. And the phase response will be changed by angle of h of e to the power of j omega. So before going into the derivation, it must be mentioned that the derivation will be shown is only true for stable system and is whatsoever not true for marginally or unstable systems. So here on forward, all h of z must lie within the ROC of z. Very well. So we can simply write z to the n when given as input to a system. The output will be h of z to the n. Just a symbolic representation of this figure over here, where we use the double arrow mark to determine the system as a symbol. So then we all know we can write e to the power of j omega n to be equal to, if e to the power j omega n is given as input, then the output will be h of e to the j omega times the input e to the j omega n. And similarly, if an input of e to the power minus j omega n is provided to the system, the output will be h of e to the minus j omega e to the power of minus j omega n. And this can be otherwise stated because z can be replaced by e to the power of j omega, which we have proved in our study of Z transform. So if that is the case, moving along the derivation, we can write from the Euler's relation. So cos of omega n using Euler's relation can be expressed as e to the power j omega n plus e to the power minus j omega n divided by 2. So by the virtue of our cross multiplication, multiplying both sides by 2, we get cos 2 cos omega n to be equal to e to the power j omega n plus e to the power minus j omega n. So now, as I have shown earlier from this two expression, if the input is given as e to the power j omega n, so the output will be h of e to the j omega n times the input. So we can simply replace e to the j omega n by h of e to the power of j omega. This in this case will be the system output. J omega e to the power j omega n plus h of e to the power negative j omega e to the power minus j omega n. So now h of e to the j omega n e to the power j omega n remains as it is. What I am going to do is simply write this expression as h of e to the j omega e to the power j omega n as its conjugate. And this is quite evident from the property, because say if we take a complex number a plus jb and take its conjugate, this will be equal to a minus jb. Now in other words, we can write a plus jb as a, say this is the vector or complex number termed as a, and this is a conjugate. So a can be written as amplitude of a e to the j angle of a. So a conjugate of this term will give us modulus of a e to the minus j angle of a. So it is quite mathematically logical if we write this expression as a conjugate of the expression provided over here. Now these two expressions when added up will become twice the real part of h of e to the power of j omega e raised to the power of j omega n. And this is also quite mathematically correct if you look, because if we take a complex number a plus jb and its conjugate a minus jb and simply add them up, what will happen, we'll get 2a over here, the jb and jb part will get cancelled out. So all we are left with is the real part of the complex number multiplied by 2. So that is what it is done over here. So finally we can write cos omega n to be equal to h of the real part of h of e to the power of j omega e to the j omega n. Just cancelling this 2 out from both sides of the equation. So let me write it down once again. Cos of omega n is equal to h of e to the power of j omega n. So since here h is a function, I'm sorry, there seems to be an r missing. Since h is a function of e to the j omega, which is in itself a complex quantity. So h of e to the j omega will also be a complex quantity and can be written in terms of the polar notation, or rather than the exponential notation, where h can be written as h of e to the j omega modulus e to the power j angle of h of e to the power of j omega. Fair enough. So now let us replace this h of e to the j omega in this equation. So we can write, well, from the right hand side I'll start r of h of e to the power of j omega times e to the power of j omega n can be written as sorry, r h of e to the power of j omega, or rather its magnitude, times e to the power of j h e to the power of j omega, the angle, times this expression where it is mentioned as e to the power of j omega n. So now simply we can multiply these two exponent terms and we will get the real part modulus of e to the power of j omega times e to the power of j omega n plus angle h e to the power of j omega. Just simple multiplicative property of two exponents. Now what shall we do is expand this term. There seems to be a bracket missing. Expand this term regarding the Euler's equation. So we will get r h of e to the power j omega remains as it is as the modulus. So we will get this as cos of omega n angle h of e to the power j omega and plus j sine of omega n angle h of e to the power of j omega. So now what shall we do is separate the real terms from the imaginary terms, so it is quite clear. Let me write it with a different color. The modulus of h of e to the power j omega will always be a real quantity. There is no doubt about that. Cosine of this value will also be a real quantity. Since there is no j terms present over here, only imaginary quantity will be this part. So this is our imaginary quantity. So now what we are concerned is with the real part of this whole expression. So this whole expression will decompose to h of e to the power of j omega's modulus times cosine of omega n plus angle h of e to the power of j omega. So we can write simply cos of omega n will have an output h of e to the power of j omega cos of omega n plus angle h of e to the power of j omega. So we have found a proof, or we have derived, that if we give cos of omega n as input to the system, the output will be shifted or changed in magnitude by the amount of h of e to the power j omega, and the phase will also be changed by an amount of h of e to the power of j omega's angle. So in summary, we can write that the amplitude and phase of the system, of rather the input, will be modified. So this derivation is generalized for any LTI, that is the linear time invariant systems, and discrete in nature, of course. And since our filters that we'll be designing or studying is a part of our LTI system, this derivation also holds true for the filtering aspects of our discussion. So now let us move on to a mathematical example where let me write the example. Where we are to describe the frequency response. So describe. One thing I forgot to mention, the frequency response is broadly divided. The frequency response is divided into two parts, and that is all known to us: the magnitude response and the phase response. So describe the frequency response of the LTI system given by y of n to be equal to, y of n minus 0.8, y of n minus 1 is equal to x of n. So let's go to the solution. So here our task is simply determining h of omega modulus of h of e to the power of j omega, or we can simply write it as h of omega the angular response angle h of e to the power of j omega, otherwise can be written as angle of h of omega. These are some difference in notations, you can use any one of them. So these are our final tasks. So this is our frequency response as a whole, this is the magnitude response, and this is finally the phase response. So in order to get to these values, first what we need to do is apply the direct Z transform for this expression. So the expression will stand y of n Z transformed will become y of z minus 0.8 times z inverse 1, since it is delayed in the time domain by a sample 1. So in the z domain, term z inverse 1 will be multiplied times y of z, and x of n will have a z transform of x of z. So now we can write y of z, taking it as the common factor for the expression, minus 0.8 z inverse is equal to x of z. Or we can write y of z over x of z, that is dividing both sides of the expression by x of z, to be equal to 1 minus 0.8 z inverse. This is nothing but our system transfer function, or the system gain. So we have found out the transfer function of the system. Now all we need to do is find the frequency response, where simply what we can do is just replace z equal to e to the power of j omega. This will give us the frequency response. So h of z will become h of e to the power of j omega, or h of omega, which is equal to 1 over 1 minus 0.8 e to the power of minus j omega. So this is our required frequency response. Now further some calculations need to be done in order to determine the amplitude and the phase response. So now h of e to the power of j omega can be written as 1 minus 0.8, just expanding this exponent in terms of the Euler's relation, cosine of omega minus j sine of omega to the power of minus 1, since it is divided by 1. So now what we'll do is take the real part and the imaginary part and make a separation between them. So this will become 1 minus 0.8 cos of omega. This is our real part, minus j sine omega inverse 1. So we have separated the real part and the imaginary part. So let's move on to the next page. I'm running out of real estate to write. So in order to determine the magnitude of h of e to the power of j omega, which is nothing but equal to magnitude of h of omega, these symbols are interchangeable, and I will sometimes use this symbol or this symbol in the future. I hope you will understand it. So this can be written as, let me do one line over here, 1 over 1 minus 0.8 cos of omega minus j sine of omega. Now in order to determine the magnitude of a fractional value, what we need to do is simply determine the magnitude of the numerator and the magnitude of the denominator. So the magnitude of 1, which is 1, magnitude of 1 will be 1, since this has not got any imaginary part, and the denominator, what it will have is root over, because the magnitude of a plus jb is equal to root over a squared plus b squared. So this will be root over 1 minus 0.8 cos omega squared plus 0.8. I'm sorry, there seems to be a mistake. Once there will be a 0.8 over here and a 0.8 over here, since we have multiplied 0.8 to both sides. So here it will be 0.8 sine omega squared. So now working with the denominator, we get 1 minus 0.8 cos omega squared plus 0.8 sine omega squared. This is equal to 1 minus 1.6 cos omega 0.64 cos squared omega plus 0.64 sine squared omega. This simply expanding this expression by the formula well known to us, which is a plus b whole squared, rather a minus b whole squared. Now 1 minus 1.6 cosine of omega, taking 0.64 as a common factor, we get cos squared omega plus sine squared omega, and cos squared plus sine squared of the same angle will yield the value of 1. So we are left with 1 minus 1.6 cos of omega plus 0.64. So the final result, or the magnitude response, is 1.64 plus 1.6 cos of omega, and h of omega's magnitude will become 1 over root 1.64 plus 1.6 cos of omega, which is our required magnitude response. Okay, if that's the case, let us calculate the phase response of the system. So the phase response of h of e to the power j omega is equal to h of omega, just difference in notation. Let me get this out of the way. Can be written as the angle of 1 by 1 over 0.8 e to the power of j omega. So in case of determining the argument of any complex number in a fractional form, what we need to do is determine the argument of the numerator and the argument of the denominator and simply subtract it from one another. So this can be written as angle of 1 minus angle of 1 minus 0.8 e to the power minus j omega. So the angle of 1 will be 0 since it has got no imaginary part, and angle of this expression, once again just expanding it using the Euler's relation and separating the imaginary and real part, we get angle of 1 minus 0.8 cosine of omega being the real part minus j 0.8 sine of omega, which is the imaginary part. So 0 minus, now the argument of a complex number, say a minus jb's argument, can be given as tan inverse b by a. So you're simply going to do that. Tan inverse, the value of b is 0.8 sine of omega divided by the value of a is 1 minus 0.8 cosine of omega. So finally we can write angle h of e to the power of j omega is equal to minus tan inverse 0.8 sine of omega over 1 minus 0.8 cosine of omega. So this is our required phase response of the system. So our task is completed. I hope you have understood the problem.